Okay.
Okay, Alex Fink will continue his lectures.
All right. Thanks. So I've substituted the symbol QM that I defined last time in the title of my talk. So I gave sort of the realizable proof sketch last time, and this time will be a focus on the combinatorial objects that arise when you're doing the non-realizable thing. So I guess the plan, I have 3 objects or things to introduce. The one we saw was the complex that you got in the realizable proof that we want to generalize, which, okay, we're going to call the external activity complex. So what I did in the realizable case, I took 2 linear spaces, 2 linear subspaces of Cn, made a bundle, did the Kempf collapsing, projected it into the fibers, did an initial degeneration, got a square free monomial ideal, and this was the Stanley-Reisner complex of that. And so the complex is one that is just matroidal, so I want to say what it is. It's going to be defined in terms of a matroid that you put together out of the 2 given matroids. D M1 M. This is not depend on the monomial weight order. This one does. And then, well, the fact that we are using to we want to do a computation that will involve these product things, but I guess I will label this section this way, the theorem. Okay. Again, for K polynomial, read Hilbert series if you like. If you take, I wrote this down briefly last time, if you take this simplicial complex, compute the finely graded K polynomial of the associated ideal. So this is just some like generating function for the faces with a variable for each vertex is what I mean by finely graded. There'll be 2 n variables. Is valuative in M1 and in M2 separately. Bivaluative is the way we say this is bilateral.
You really mean Z2n graded, not Z2 times the n?
I mean, yeah, really you can do this with Z2n graded. We don't need much more than the Z2 times the n grading because the natural grading from the group action is Z2 times the n, but even this is true.
Is that, but it depends on W.
But it depends on W. Right, so fix W. That's that thing. And yes, and maybe it's worth saying now before I hop in that the what we do with this, so just to kind of this is not a part of the plan, but the reason that we're doing 3 from the point of view of what I did last time. Last time, once I did this initial degeneration, I had to use this Conca de Negri-Gorla machinery to connect this ideal to the ideal of a single matroid Schubert variety and use this relation to a single matroid Schubert variety to conclude what I want to do about this ideal. And, that's the step that you extend by valuation. The input to their theorem is if you have 2 ideals with matching Hilbert functions, then bada bada ba happens, right? 2 ideals with matching Hilbert functions, and one is in fewer variable than one is the gin of the other, and you get a lot of consequences like Cohen-Macaulay and transfer of free resolutions, and that is kind of where we use the valuativity. Since the Hilbert functions are valuative, this applies to the ideal of this simplicial complex in all cases, and you get the same. Whether or not it was representable. So the kind of the end of part 2 and part 3 of what I said yesterday just then applies in complete generality. So what you get, so you get consequences like, the any given, well, I guess if, because of some Alexander duality, like top looking wedges that correspond to the last stage of the free resolution. This thing is an explicit sum of dimensions of homology of links, which I can write down if people are very interested. But I'll just write it symbolically for now. Sum of dimension of H. Well, this is like rank D minus 1 in homology of links of that. And you get other consequences like that the complex is Cohen-Macaulay in all cases. And various other things that come from the package. So sort of once you know this, you just use it to rejoin the realizable proof just in the point we were using these results. Okay, but let's start with the plan. Okay, so part 1, I want to define the diagonal Dilworth truncation. So that's going to be a matroid that you make from the 2 given matroids. And I guess I'll start to convey the idea. I want to start by saying what it is in the realizable case. So this is some, Dilworth was looking at things like this in 1944. I think he wanted to make an operation that was like truncation on the lattice of flats, but where you cut out the low stuff instead of the high stuff. And okay, so what you can, here it is in the realizable case. Okay, so I want to think of my realization. So I had a linear space L that was in a vector space, K to the n. Right, and I said you can think of this thing as a hyperplane arrangement. So I want to think of my realization as the collection of all of the coordinate hyperplanes, because this L lives in K to the n, and then I can intersect the coordinate hyperplanes with a good hyperplane arrangement. That's why I want to look at my realizations. Okay, so if I have L1 and L2, so given L1 and L2, a realization of the Dilworth of L1 and L2, what do you do? So sort of, okay, the first step is to take L1 direct sum L2, and let's not take a hyperplane arrangement in it, HI1. Let's take an arrangement of codimension 2 subspaces in it. That is, in some sense, the only natural thing to do with the direct sum. So now I have a codimension 2 subspace arrangement in here. Okay, I don't want a codimension 2 subspace arrangement. I want a hyperplane arrangement again. So I'll just, mod everything out by a generic element. And okay, generically, the image of these things, okay, well, I guess I can't say this mod LFL doesn't apply in here, but the image of this, the image of this subspace under the quotient by L in the big space will generically be, for a generic choice of L, this will be the same dimension. This won't drop in dimension when I look at the image in this quotient. So now this thing, maybe I should just say the image of this, not the quotient. The image of this thing will actually be a hyperplane in this quotient of this by 1 dimension. So that is how you realize the diagonal Dilworth truncation. It's, something like, okay, we kind of went up to polymatroids where the elements have rank 2, and then we quotient down once to get the ranks down to 1 again. So we need a few of the properties of this guy. So section 4 of our paper, it starts with just going through various circuits and rank function and independent sets and so on. And so I should probably say a couple of those here. Let's define it. I think I'll say two and allude to a third. Okay, so I'll define it in terms of the independent sets. In terms of the independent set, so let the IP of M will be my notation for the independent set polytope. Dependent set polytope. So just the convex hull of the indicator vectors of the independent sets. So I had the basis polytope last time. You just kind of take all the points with non-negative coordinates that lie underneath the basis polytope and that set polytope. Then, okay, the definition of this matroid is going to be that through its independent set polytope, I take the Minkowski sum of the given independent set polytopes. That corresponds to like this kind of, I've added the rank functions because I have this arrangement of codimension 2 subspaces. This sum of polytopes corresponds to summing the rank function. Then I want to drop it by 1. The way I drop it by 1 is I just take out an independence polytope of U1n, right? So this is the convex hull of 0 and the standard basis. Not like virtual polytope Minkowski difference, but really like the set of translates of this that live inside here. Okay. There's one case this doesn't work. What if there's no translates of this that lie inside here? Well, that will only happen if there's a loop, it turns out, right? If I is a loop in both matroids, then all the independent sets will have the xi coordinate equals 0, and you can't fit this in. Okay, so that's the only case in which this doesn't work. So if M1 and M2 have no common loop, then an independent set, right? We can read this. An independent set of the Dilworth is anything which, no matter what element I add to it, can be an element that's in there already. I can make a multi-set with a coefficient of 2, or I can pick a new element. But no matter which single element I add multi-set wise to it, I can partition it into independent sets for the M1 and the M2.
So really sorry, Alex. So on the right, I think this is a definition we saw. I mean, this somehow doesn't change the set, but on the left, the one you gave with L1 plus L2, it looks for me that you double the number of.
I did not double anything. Sorry, this is just meant to be indexed by the same ground set because I had n hyperplanes in each one, and I took n codimension 2 things, and then I looked at their image under modding at one thing. Okay, so there's just n things. Dilworth is interested in the case where you got there to be 2 n things. The diagonal is kind of, we're looking at the diagonal of the pairs of the bases. It's okay.
Thanks.
Yeah. So yeah, this is a matroid on n. So you start with matroids on n, and you end the matroid on n. So this is some kind of, if you've seen matroid union, it's a bit like matroid union. Matroid union would be just be if I didn't do this, but I just like took this and then like cut away the points with a coordinate greater than 1. Independent sets in the matroid union are unions of independent sets. I want things which no matter what element you add, you have a multi-set partition into 2 independent sets. So I guess I'll give an example. Maybe I'll go over here. I mean, maybe the first thing, the first example I want to give is that if I take any matroid and put U1n in here, I get my original matroid back, right? Because if I take an independent set in M, I have any other element, well, I just throw that in here, it's independent, and I get my original set back. if I have a dependent set in M, I can add an element that's in its closure, maybe a repetition, and then I can't do that. So if I make one of the matroids equal to U1n, then that's the identity for this operation, such as it is. U1n. And so we use this to recover the matroid Schubert variety, right? This is going to be the matroid Schubert variety case. Everything we do today, if I put one of the matroids to be U1n, I should be doing stuff for the classical matroid Schubert variety.
Maybe you explained this, but I didn't catch it. What does that minus mean?
This is the set of translates. Okay, so what I mean by P minus Q should be the set of all vectors in the ambient space, so that Q plus U is a subset of P. So if Q was a Minkowski summand of P, then this will recover the other summand. But if Q wasn't, right, if there's some corner of the wrong shape in P that you can't, shove Q into, it will kind of be the like effective divisor part of the difference of divisors, if you like. So yeah, I wrote this in terms of polyhedra, but yes, you can interpret this in terms of partitioning sets into independent sets. I guess another kind of example, I'll put just kind of, okay, let's say I just put in two uniform matroids. Well, what do I get? Okay, here for a set to be independent, here it just needs to be rank, or only the size matters. Size at most R1, size at most R2. Okay, so any set that is size at most R1 plus R2 minus 1, then when I stick one more element into it, I can do the partitioning. So it's just, it's just about the sizes. In this case, I'm going to get R1 plus R2 minus 1, right? So this is kind of a good example to keep in mind, both because this is the typical size, this is the typical rank, the typical way the rank of the output behaves in terms of the inputs. It can be less, but this is kind of the geometrically nice behavior. And well, if there were little dependencies in here, they might also wash out. Like if I took two phonomatroids, D of them would be uniform again. It kind of takes simultaneous significant dependencies in these two for a dependency to show up in the output. Okay. And I guess I want to say one other fact about this guy, which is its circuits. So the circuits. The circuits are going to relate directly to the equations of the y-hat variety from last time. So that's why I want the circuits. Minimal non-empty set C. So that if I look at the rank of C in both matroids, the sum is exactly the sum of C. Right, okay, so in this uniform case, right, so the circuits of this are sets of size R1 plus R2. This rank function tops out at R1, this rank function tops out at R2. The sum of the two rank functions tops out at R1 plus R2. I mean, it reaches that value when you hit max of R1 plus R2, right? When you hit max of R1, R2, the rank function is R1 plus R2, but then it stays there, right? So then I start bumping up the size of the set. The moment I hit R1 plus R2 is when the size of the set is R1 plus R2, so that's the circuits I get here. Right. The reason it's nice to have these circuits is because, yeah, they're the ones that encode the equations, and these are supposed to be, right, this is supposed to be an initial degeneration of my y-hat. So, well, let's move on to that. Okay, so I'll say what it is. And actually, maybe I'll say what the equations of the y hat are first. So motivation, kind of, or like the realizable motivation that we're trying to follow. Okay. So a universal Ribner basis for our y hat from last time. This of a bunch of determinants. One of them for each circuit of D. That is where this thing comes from. What are the shape of the matrices I'm taking the determinant of? Okay, well, if I've got a circuit C of D, let's call it C. Okay, so if I've got a circuit C of D, so I've got some matrix, say the columns, if I use, matrices where the columns index the graph, that which is the convention I've been using. So then the columns of this matrix are indexed by C. And I'm going to have a part of this that comes from N1 and a part that comes from N2. Okay, well, if I look at the restriction of M1 or L1 to C, I'm going to have some linear space of rank M1 of C. And if I look at the restriction of L2 to C, I'm going to have some linear space of restriction rank M2 to C. And so, this condition is what ensures that I'm taking the determinant of square matrix when I put these things together. And now I'm going to have, I take my matrix that realizes this and I multiply it sort of column-wise by x's. So this top blocks, let's say I have matrices A and B. So A is a matrix for like L1 restricted to C, B a matrix for L2 restricted to C. I put A in the top, but then I multiply by like a diagonal matrix of x's for the variables in C. And here I multiply by a diagonal matrix of y's for the variables in C. All right, so the top part has each thing is x times a scalar. The bottom part, each entry is y times a scalar. I take a determinant of this. Each term in the expansion of the determinant has a monomial, which is, Zn degree C, but might get an x and I might get a y for each of the elements of C. I'll get an x this many times and a y that many times. And they'll sum to the size of C. Right, so it's it's exactly this condition that says it's the first time one of these determinantal conditions could possibly show up for the restriction of a given subspace. If you take a coordinate projection of your y, the smallest coordinate projections where you could have an equation are these ones, because the kind of equation you should get, England says, are determinantal equations like this. So that's where this thing comes from. So these determinants are going to be our equations in the representable case. And I said these are going to be universal Ribner basis. Okay, so what are the terms of these things? Well, the terms of these things are going to come from terms of the Lagrange expansion into this group of rows and this group of rows, right? So a typical term will have a determinant of some like square, like rank M1 many columns up here, and the determinant of the complementary rank M2 many columns up here, right? So the terms are all going to be in the form scalar times, some x's times the complementary y's. So those are the initial forms of this thing. So that motivates where we're heading by defining this W, right? So what we want to do is pick one of these initial forms for each circuit. That's why we want to define this delta W. All right. So how does that go? So I need to use fundamental circuits to define this complex delta. This is kind of a, right? These things, if these are the generators of the ideal, they should be the non-faces of the Stanley-Reisner complex. I want to tell it to you by faces. So if I could tell it to you by non-faces here, actually, maybe it's worth doing it. Maybe it's worth doing it both ways. Okay, so kind of let's define it through its non-faces, and then we can make a theorem about the faces. Okay, so is the simplicial complex. On, well, I have n x's and n y's. These are what I'm using at my vertices of my simplicial complex. Well, you can leap in a different way. I'm identifying things with monomials here. There are faces of a simplex. Well, what are the minimal non-faces? Well, they are the, okay, I have x times some set. Let's write it like x super I. This is like multi-index notation, the product of the xi's in this set. And then the product of the xi's in this set. Okay, where I1 and I2 have a disjunct union, which is a circuit in this matroid D. What else? I1 should be independent in M1, and I2 should be independent in M2, because if they're not independent, the minor I'm trying to pick out is 0, so the term doesn't show up. So I need each one to be independent. And, well, I need some counterpart of the W initial condition. So I'll just say by force, right, that the W weight of xi1, yi2 is maximal, subject to the above. I fix for C. So for each circuit, I have some maximal coloring of the circuit by x's and y's, and that is one of the minimal non-faces. And okay, so having prescribed that, right, there's, I can try to describe this thing both by minimal or minimal non-faces and by facets, maximal faces, and there will be some duality between these corresponding to the circuit basis duality for a single matroid, right? The circuits, if I give the independence complex of a matroid, the circuits are the minimal non-faces. So I should expect something basis-like as the facets. And so indeed, we get something basis-like as the facets. All right, let me make a definition, just a definition running off of this. You do this kind of thing in usual matroid activity. For usual matroid external activity, I have a basis and I look at the fundamental circuits of an element with respect to that basis, and I ask, is it the minimal element of its fundamental circuit or not? That is how you define usual matroid external activity. Right? Can you swap it with anything smaller is the same as saying, is it the minimal guy in its fundamental circuit? Okay. Well, minimal guy in its fundamental circuit is just like, well, you pick some Lex order and then you have just one Y, and then that tells you where the Y has the minimal weight. Okay, so you can rephrase that this way. So this is a generalization of matroid activity. So our definition is, you know, let's say I pick one of my matroid indices, 1 or 2, and I'll say be a basis of D. I not in there, and I take the fundamental circuit. So there's a unique circuit that contains I and is contained in B union I. That's the fundamental circuit. I want to say, like, which, whether it ends up as an X or a Y in here, is an activity statistic. So I say that I is like K active, so either 1 active or 2 active with respect to B. If I is in the K side of this initial partition.
Only depend on the relative ordering of W.
This depends on more than the relative ordering of W. So this is not a permutahedral type of thing, right? Like I can have, so among these decompositions, you can think, okay, so I'm looking at the ways to decompose C into 2 sets of prescribed sizes. There are kind of permutahedral in many of these things. You know, maybe there's an octahedron in many of these things. But then I'm doing, well, this has to be independent and its complement has to be independent in an unrelated matroid. So I'm doing a matroid intersection. And so my matroid intersection, it will always be a lattice polytope. That's the matroid intersection theorem. But you know, maybe that is dependent in one and this is dependent in the other. So I take the matroid intersection and it's not a matroid anymore. So I can have just like any normal fan to a 0,1 polytope more or less can show up here. So yeah, it's not dependent on much more than the relative order of the variables. Okay. So now I want to make the external activity complex by its faces. So the facets of this external activity complex are, well, there's going to be 1 for each basis. And what do? The basis you take in both colors. If you've seen the Ardila-Booker external activity complex, this should be reminiscent of it. But I take the basis in both colors. And then, right now I have the basis in both colors. If I look at the basis and 1 more element, I should have 1 equation that excludes something for that element. So now I should take that element kind of in the wrong color. So I should take like the X's. Did I get my convention correct? Okay. In order to match the paper, which I should do, right, you have to exchange things. So apologies to those taking notes in pen. In order to match the paper, I want to do it this way around. So then here I can say, right, so the 1 active ones are the ones that show up as a Y here. So I want to exclude them being an X. And here, the 2 ones show up as an X, so I want to exclude them being a Y. So, okay, apologies that I messed up my convention on the go, but there is going to be some sort of, like, if it's an X in the non-face, then it's a Y in the facet and vice versa. So there's going to be both conventions going the way we actually did the paper in this convention. So apologies. I want YX up here and XY down here.
How possible is it to do a concrete example?
We can do a concrete example. We can do a very concrete example. So like we could do, let's do like a couple of uniforms in a like a very Lex weight order so that nothing funny is. Okay. So let's do like U2N. Let's do U2N, U2N, where like the weight of X1 minus weight of Y1, I guess I can write that as a ratio, is much bigger than X2, which is much bigger than Xn over Yn. So I kind of want to make 1 an X at all costs, and subject to that, I want to make 2 an X at all costs, and so on, if I'm getting in the greatest term. So if these are much bigger than, you know, much bigger than, not just necessarily bigger than, so I can really do it lexicographically. Okay, so now what are the non-faces going to be? Okay, so minimal non-faces. Well, I have to take circuits of D and color them. D is U3N, so circuits of D are 4 sets. And so now I want to color my 4 set. I want to break it into independent sets. So those are going to be size 2, independent sets of the restrictions, a 2 set and a 2 set. And I want to do it in the way that the x's in the second set are the maximal way. X's in the second set, one in the first set is the maximal way. Okay, so I said my low numbered x's are very big. So I want to put low numbered elements in the second set. So if I have this circuit, I'm going to get, if my circuit is like I, J, K, L in that order, then the non-face is going to be, I put Y's for these, sorry, I want to make it Y's for I1, X's for I2. So I1 is going to be KL, I2 is going to be IJ. So I get like XI, XJ, YK, YL. All right. And so then what are the faces or the facets of the complex going to look like? So for each basis, bases that you forget are 3 sets. And so I get my 3 set in both colors, X and Y. And then I put either an X or a Y in for every non-element of the basis, depending on what dodge the circuit of this form. So if B is, the bases are in fact the sets of 5, 3. So if B is like something like this, all right, then I'm going to get X, I, Y, I, X, J, Y, J, X, K, Y, K. All right. Now for stuff less than all 3 of them, I don't want to make the pattern X, X, Y, Y. So all these variables will just show up just with a Y. Okay, for the stuff in here, I still don't want to make X, X, Y, Y. So these ones are also a Y. Here, though I don't avoid making X, X, Y, Y. Now Y is bad here. Now I have to make these ones an X. And these ones similarly, I don't want X, X, Y, Y. So these ones have to be an X. So that is what the facets look like. My basis has both colors and the other elements have the colors that let me avoid the circuits.
What's an active element again?
An active element, I call each element 1 active or 2 active according to whether it gets in I1 or I2 up here. So like these ones that end up in as an X, I call them 1 active because they'd be an I1 in the circuit. Because I call them 2 active because they'd be an I2 in the circuit. The usual notion of active, maybe it's worth writing down, like special case, usual matroid activity. So this is the case. The Dilworth complex is the external activity complex for the usual activity. So I put the second matroid U1 in. And now now if I have the initial, now in this case, only the relative order of the variables in W matters, right? So if I have, let's say the same W, well now any circuit, the non-faces. What am I going to do? I'm going to take a circuit of M1, that's the only part of which the data left. And I'm going to color everything. Only one of them is going to be an X because my independent set, I forgot to switch it in both places. Only one of them is going to be an X because my independent set for the second matroid can only hold one element. Only one of them is going to be an X. And in this term order, it should be the least index, which goes into an X. So it will be X for the minimum of C and Y for everything else. Right? And then we usually say, so, you know, the standard definition, the classical, is that an element is externally active I is the minimum of its fundamental series, which is the same thing that I'm now calling Q active here, that it goes in I. So that is how it's a generalization of usual matroid activity. All right. Any questions before I go on to part 3 of the plan? Okay. So part 3 of the plan is to compute the K polynomial of this complex. And sort of this Kempf collapsing Weymann's geometric method package, right, tells you that, okay, the K polynomial, you can get it from a free resolution. You could get a free resolution from all of these wedges of bundles. But wedges of bundles are related to Chern classes and Segre classes, right? Chern classes are about simultaneous vanishings of sections. Segre classes are about, like, you take hyperplane sections of the total space of the projectivized bundle, and both of these are governed by behavior in wedge powers of the bundle. So you can look in section 3 of the paper for, like, the precise results, because I'm not actually using this, but as motivation, right? The fact that we want to compute this K polynomial by Weymann says we want to compute things about, so like just why, you know, why do what we're going to do? You know, why do what's coming? Kind of this Weymann method says that you see these, like, wedges are in the free resolution for delta. And then these tensor products of wedges should correspond to products of Chern classes. And Weymann can tell you precise ways in which should correspond is true, but I'm not going to use these precise ways. It's at least motivation that this should correspond somehow to products of Chern classes. Of the same bundles. So if we wanted to compute this, you know, it might be natural, and indeed by this kind of Weymann argumentation, we thought if we want to compute this K polynomial, maybe we can compute it by intersecting these Chern classes. Well, 2 Chern classes. To intersect 2 things, one approach is to realize these both as Minkowski weights and use the fan displacement rule. Right, so we use the fan displacement. And the displacement is exactly going to be W. If we regard W as a weight order, some sufficiently generic weight order that it actually gives you monomial initial ideals, then what we're actually going to do is take the Bergman fan, not the Bergman fan, the Minkowski weight for this Ci. So I'll have some fan here, which is, this fan is the Minkowski weight. I should do this in color. I can use white and yellow. This is going to be the Minkowski weight of this. But the point is going to be like the X part of the weight. I will translate it there. And then for the other fan, point is going to be the Y part of the weight. And so I take that Minkowski weight for the Chern class of the second one. And then I do some tropical intersection.
How does the generosity conditions compare?
We basically waved our hands about this, but I think the generosity of this should be the same condition as like monomial initial ideals and all of these. I think that's what will happen. So then this is an actual, set theoretic intersection we can do. All these weights, I'll describe what these CJs are, but all these weights are one, all the weights on at these points are going to be one. So we can really kind of think very set theoretically when we try to do this. All right, I started about 15 past, I'll go to about 15 past. Right, so what I want to say is I want to give you the description of what these Chern classes are. Like similar description to the Bergman fan as the coming from the lattice of flats. And then I want to show you some graphs that you can use to work out what intersections are here. Okay, so this is a theorem from the Berget Eur Spink Tseng paper that tells you what these Chern classes are. And just so I get the indexing correct, okay. So these are permutahedral objects, right? So this Minkowski weight, the Minkowski weight of one of these Chern classes of any Q of a matroid, I guess we have a dual here on a permutahedral cone. The cone corresponding to, I have flag sets. So I can describe my cone in the permutahedral variety as flags of sets that way. Well, it's an initial matroid. If I had said the top Chern class here is the Berget class. Maybe up to dual. I think I want it this way now.
Q check is negative.
Q check is negative. I want it this way. That's right. So the top Chern class here, okay, right. This just matters up to signs, and there were sign alternations in the stuff I was talking about yesterday. So we'll work with cubes, and then we'll deal with the signs by working with cubes. Okay. So this is the Bergman class. If I take the top Chern class, and what's the Bergman class? It says that, well, each of these should be flats. And so you can, if I had a maximal cone in the Bergman class, it would say that each of these were successive flats. And then if I take the minor between two of these, it would be a uniform rank 1 matroid. So it'd have a chain of uniform rank 1 minors. To get to the Chern classes, in general, you just have to introduce some loops. So the weights are either 1 or 0. When are the weights 1? All the minors, again, they should either be, you restrict to one of the S's, and you function out the previous S, are rank 1 uniforms. That would be the Bergman class case, or loops. And the number of loops governs how many sets are in the chain, or single loops, right? I can have one loop at once. I can have one loop at a time, and the number of loops I have is governing the dimension of the class. And so as you vary it, you get different Chern classes. Exactly co-rank M minus J on the Marlin list. So I take All right, I take sort of, since I'm gonna want to look at two of these things, let's say I have the kind of thing I want to do. Let's just kind of, say I have a rank 3 matroid. And maybe I have a chain of flats, where like, I don't know, 1 is contained in 5, is contained in 3, and this is gonna be the ground set, this last one on 10 elements. So, okay, if I had a point in the Bergman fan, it would look like, I will draw like a sort of all right, here's my real number line, and I'll draw the coordinates of such a point. Well, if I had a point on the Bergman fan corresponding to this flag of flats, right, that says I'd have something times E1 plus something times E1, 2, 3, 4, 5 plus something times E1 to 10. Okay, if you were working like in the modulo quotienting out the stabilizer, I wouldn't have all 10 coordinates, but let's just say I'm working in R10. Okay. So then like on the real number line, the first coordinate would be up here. The 2nd through 5th coordinates would be here. And the 6th through 10th coordinates would be here. Let me put these above for reasons. So this is what a point in the Bergman class would look like. Okay, this is rank 3, so co-rank 7. So the Bergman class is Q7. And then, well, if I want a class in, say, let's say Q4, so 4 QM, 7 minus 4 is 3, so I have to make 3 loops. How to make a loop? I just like take an element, like let's say take an element 10, and I'm gonna like make it show up separately in the chain of flats. So now I get up here, this restriction is still uniform of rank 1, but then after I have a loop. 10 is in the closure of this, so when I look at this minor, 10 is a loop. Let's pull off another one. Let's pull off like 9 and make it a loop. We can pull off like 5 and make it a loop. It could go here or here or here. Let's just put it somewhere. So I've pulled 3 elements off of the flat they were supposed to be in, so that now when I hit them in the chain of flats, they're loops. So this is how you build a point on one of these Chern classes. You take a flag of flats, then you pull off some loops and throw them, you know, to the left on the real number.
So you're saying in particular, like the sort of the boundary of this is the Bergman fan. If you have like C n minus R minus
Yeah.
1.
That's right. So special case is C co-rank of M of QM.
But like in particular, the support of each of these fans contains the Bergman fan in its closure.
Yeah, the support of each of these things this is an increasing chain of things. Yeah, I could, right, if I pass to a boundary of this cone, I could just move this point into either the joining sets. So, you know, a general point of this fan might not look like this, but kind of a point in the interior of a face actually looks like this, that you see only these co-rank 1 things in the flats. This is a property that we call Chern generic in our paper, right? Something's Chern generic if it's in the interior of the face of the Chern class it should be on, so you see only rank 1 uniforms and loops.
Are you producing sequence of elementary quotients that ends with matrix?
Yes. Well, yeah, I guess there's elementary quotients and then there's like throwaway element. So if it was the Bergman class would just be elementary quotients. But since I'm quotienting out these elements, right, the ground set is reducing.
And this chain is different from the usual one, like Higgs-lit or.
Oh yeah, no, in the Higgs-lit, right? I'm really quotienting out elements. So these elements I could re-add them as loops or something, but they're kind of not featuring. In the Higgs lift, I have a matroid on the whole ground set every time. Okay. So maybe I'll just say, since I've run out of time to make precise statements, I'll just say the kind of thing you do to do these intersections. Okay, well, if I have a point somewhere in this picture, right, and I want to know, I have some point P. Well, I want to know simultaneously where P lies. I can imagine not just one Chern class, but the nested family of Minkowski weights for all the Chern classes here, and the nested family of Minkowski weights for all the Chern classes here. And then I have a point, and I want to know where it lies in the intersection. On which of the Chern classes does it lie? Well, kind of in this way, I can encode, the stuff for M1 as a, the stuff for M1 by this proposition corresponds to some chain which generically should look like rank 1 uniforms and loops. And then for M2, also I should have some, let's say M2, I'll do another one of these. Maybe M2 is rank 2 and 2 is parallel to 5, so I can have 2, 5 as a flat. It's just for that. I can have the flat 2, 5 and go through everything else, and maybe I'll put 2, 5 up here. And then the rest of the stuff, okay, I'm just transcribing an example which I made up here. Not so important what it is. 1, 3, 6, 9, 10 are some of the other elements, and the other ones I pulled off as loops. Okay, in somewhere. Okay, so here, rank 2 co-rank 8 pull off 3 things here in C5. Okay, but now, right, the fact that I know the relative displacement of this fan and this fan, it's the difference of that weight vector and that weight vector. The fact that I know that relative displacement means that if I draw these two pictures, I know exactly what slope every edge has. So there's in an arbitrary point in that picture, there's always an edge for one which will have exactly this slope wherever it appears in the two pictures, right? And its translate expresses the P1, the coordinate P. And in a similar way, I can fill in a graph here. And the graphs that appear are the graphs that I can get by taking my edges with their fixed canonical slopes that come from W and putting them together into graphs so that all of the minors I see in my graphs have uniform rank 1 or loops. And so the combinatorial apparatus is basically you try to build graphs that look like this, where as you work, right to left along each real number line, you want to see either the minor is uniform of rank 1 or a loop in every case. So this is a typical example. This one, okay, I have 10 edges, 11 vertices, so maybe this is a tree. In fact, it is acyclic, it's a tree. The fact that W is sufficiently generic forces this to be a forest. So I've picked one that's as connected as possible to make it a tree. And so, all right, maybe I'll just say briefly, since I'm out of time, the kind of thing you need to do to characterize the K polynomial. It turns out, for each region of this picture, you get a different set of elements which are showing up in, I filled in the ones that are appearing in uniform rank 1s and left out the ones that are showing up as loops. And the key fact, maybe I'll just write the key theorem. So for each point P, in here, I get a monomial, which I'll call MP, which is the product of all the variables that showed up in rank 1 flat. Instead both equals product of variables in rank 1 minors. So in this case, the MP, what would it be? Okay, on the one side, I took 1, 2, 3, 4, 6, 7, 8. And on the 2 side, I took 1, 2, 3, 5, 6, 9, 10. And then the theorem is that delta W of M1 and M2 is exactly the like downward closure of the set of all of these monomials. So every facet appears as such a monomial, and everything that appears is a face. Not all the faces appear, but every facet appears.
Which Chern classes are you taking?
So which Chern classes am I taking? If I want to pull out a Chern class of this, well, then I want to look at trees like this where I prescribe how many loops are here and how many loops are there. And that tells me this Chern class times that Chern class.
So you look at all possible Chern classes to give you.
That's right. So the number of facets of this of a given Z2 degree is the product of Chern classes at dot degree. Yeah, so section 6 is all about like how you prove this. Basically, you take a graph like this. Maybe it's not a tree. Well, it's not always a tree. It's a tree if the rank of D is maximal rank. Otherwise, maybe you can't get this all connected. You take some graph here, you study like how you can slide around the different connected components and smash them into each other. And then once you've got some maximal thing here, like, okay, why does this correspond to a basis of D? Well, a basis of D is something that no matter how you add one element, you can partition it. This is a tree. No matter how I add one element, I get a graph with exactly one cycle. This should correspond to 4 because 4 lived here and 4 lived here. So I added a copy of 4. I get one element. And then since this is now a graph with exactly one cycle, I can direct everything toward the cycle along the tree. And now the direction, each vertex has one out edge, and that tells me my partition. And on the cycle, you choose it, right? Like the cycle, one edge of the cycle really belongs over here. So you choose the orientation of the cycle that would go out into the one that's really not in the cycle. And then that, you work through the arithmetic of the translation to this, and that gives you this activity condition. So in fact, these graphs are exactly encoding both the circuit and the basis presentations of D. I'll stop there.
Questions?
Okay.
How to think about this picture in relation to that picture?
So I guess there's a paper of Federico, Kris, and Raul Penegiao that have these pictures, and we call them intersection graphs. Or they call them intersection graphs, if that's what you were asking. I don't know if that was your question.
It sounded like for each region of that.
For each point here, you get a graph. But if the point moves within a region, all that happens is like different connected components of the graph kind of jostle without the combinatorics of the graph changing.
I see.
But if I had something disconnected here, an edge here, I could slide it without changing the way the graph looked. And that corresponds to moving in a region.
The theorem sort of reproves what Wayman tells us in the realizable cases.
Right. In the realizable case, it turns out that we kind of Alexander dualized here. So we don't get the Wayman resolution. We get, okay, this is an Alexander dual to a Cohen-Macaulay complex. We get a linear resolution. And it sort of reproves the Reiner-Velker result about linear strand of minimal free resolution of monomial ideals. It's a bit funny that we see the Alexander dual picture here when we're doing this, but.
Okay, no more questions. Let's thank Alex again.